Hi everyone, and welcome to Chapter 19 again. This will be specific for sections 6 and 7. And in order to save a little bit of time, I am going to be doing the sample exercises only in this section. I'll explain the concepts as I go. So starting with sample exercise 19.10, this is on page 827. Have your calculator ready, have your guided notes ready, and here we go. Okay, so the question is, it says, as we saw in section 11.5, the normal boiling point is the temperature at which a pure solid is in equilibrium with its vapor at a pressure of 1 atmosphere. So I explained that. At a boiling point, technically it's in equilibrium until you have the entire sample vaporized. Part A. Write the chemical equation that defines the normal boiling point of liquid carbon tetrachloride, CCl4 liquid. So, that's pretty simple. Let's write the equation. CCl4 liquid is going to turn into CCl4 gas at the normal boiling point. Pretty easy. Alright, part B. What is the value of delta G for the equilibrium in part A? Alright, so part B. Oh, by the way, they said at boiling point, so sorry, it's not a full arrow. Almost forgot. Alright, so second part. Since this is going to be at equilibrium, that means that the value of your delta G is going to be 0. So the famous formula, delta G is equal to delta H minus T delta S. Remember that your G value is going to be 0. And so really what we care about is the temperature that it boils at. Don't forget. We can rearrange this formula, basically, is what I'm talking about. You can rearrange the formula to be, okay, the temperature of boiling. We're going to rearrange all of this. The temperature that it boils at will be equal to delta H over delta S. Okay, so we just need to look up some information in the back. It's 1 mole of everything. It's always, for delta H, it's always products minus reactants. So, obviously, we need to go look and find some stuff here. Okay, remember that you're looking for carbon tetrachloride in the gaseous form when you're using your appendix. Okay, for the delta H on this guy, we're going to give you all the information that we got because eventually we're going to need our delta S, correct? So I'm going to give you delta H and delta S for these guys. So delta H, 106.7. And sorry, that's negative. 106.7. Keep in mind your units. Kilojoule per mole. Delta S, 309.4. And remember, this is joules per mole K. Alright, let's look up the other guy, CCl4 in the liquid phase. Delta H, negative 139.3. And your delta S, 214.4. Alright, everything is tabulated. So now all we have to do is just make sure that we plug it all in. So remember, it's always products minus the reactants. So I'm going to go ahead and continue using this formula. So the delta H for us, the products will be negative 106.7 kilojoule per mole. So products minus the reactant, which would make us a positive for the delta H, 139.3. And remember that your delta S and your delta H have to have the same values of the joules versus kilojoules. So we need to be very careful about switching the values here, okay? So I'm going to go ahead and do the products. This will be, I'm going to switch it to kilojoules. So 0.3094 kilojoule per mole K minus the 214.4, oh sorry, 0.2144, sorry, kilojoule per mole K. Okay, your book does it in 2 different steps, so I'm just doing it all in one. So let's make sure I can get the correct answer here. So negative 106.7 plus 139.3, that's your numerator, divided by, open parentheses, 0.3094 minus 0.2144, close those parentheses. Alright, I get a temperature of 343 Kelvin. Obviously we want to change that back into Celsius, so subtract 273. I get approximately 70 degrees Celsius. Check the book. Fabulous! Alright, that was part A and part B. And then finally we got to do part C. It says use thermodynamic data in Appendix C and equation 19.12 to estimate the normal boiling point of CCl4. Oh, that's what I did. So what did I do? Oh, okay. So part B was what is the value of delta G for the equilibrium in part A? Did I do 2 steps in one? Oh, right. This has to be 0 because it's at equilibrium, and then part C is right here. Okay, got it. So part A is the equilibrium, part B, delta G is going to be 0 because it's at equilibrium, and then part C, we figured out your T boiling, temperature boiling. Okay, sorry about the confusion. Moving on. Okay, sample exercise 11 begins on page 828. It says calculating the free energy change under non-standard conditions. So we will continue to explore the Haber process again, not the first time that you've seen this. It says calculate delta G at 298 K for the reaction mixture that consists of 1 atmosphere nitrogen, 3 atmospheres hydrogen, and 0.5 atmospheres NH3. So basically what you have is the a quotient instead of the K value. So basically we can use equation 19.16, which is right there on page 827. Let me go ahead and give you the formula. It looks like this. Delta G is equal to delta G standard, right? Plus RT, natural log of the quotient value. Okay? So basically what you have is an equilibrium. You're not, you may or may not be pushing towards the reactants or the products. We don't really know. We haven't established an equilibrium yet. So they gave us the quantities of the container. So the very first thing that we're going to tackle is trying to calculate that quotient value. Remember, it's just like equilibrium. It's products on top, reactants on the bottom. So for us, we can use partial pressures, which is basically what we have here. You have NH3, so here's your NH3 value, 0.50, but don't forget you have a coefficient of 2. Make sure you square it, over, let's do your nitrogen. Your nitrogen was 1 atmosphere, and no coefficient on your nitrogen, that's nice. And then your hydrogen is 3 atmospheres, but then you've got a coefficient of 3, so you've got to make sure you do that. So let's go ahead and calculate the value of your Q. 0.5 squared divided by 1 times 3 to the 3rd. Okay, check my values here. Yep, I'm good. I got 9.259, which basically is 9.30. Anyway, times 10 to the negative 3rd value. So according to that value, who's preferred, the reactants or the products? Since you have such a tiny number. Okay, but anyway, it's technically still positive, or I mean, of course it's positive, it's Q, but it's really, really small, so it's not really preferring the making of the products. It's actually going to shift towards the reactants on this one. Alright, so here we go. Let's keep going. The formula, we got to get the delta G standard for this reaction. In order to get the delta G standard, we're going to have to do a little looky look at all of this good stuff. So in sample exercise 19.9, which we did not do, we calculated delta G. Otherwise, you'd have to grab all the information from the appendix and fill it in, but we'll just pretend that you guys looked at that. Your delta G standard for standard conditions is negative 33.3 kilojoules for this particular reaction. So we'll just go ahead and plug that in. And then now we can use this equation that I wrote up there. Now we can use it for your non-standard conditions. So here we go. Keep in mind we got to be very observant of all of our units that we used. So the overall delta G for the non-standard, we're going to use the negative 33.3 kilojoules plus the R value that you guys should be using. Be careful. This one should be 8.314. Watch your units. Joules per mole K. So what do you think I should be doing to the joules per mole K? Because look at what you got over here. You got your kilojoules over here. So if you want to convert your kilojoules, that's, you know, whatever, it's your preference. The book does not. What they do is they say, all right, there are 1,000 joules in 1 kilojoule, so they make sure that they do this conversion. You see your joules are on the numerator right there. So they just make sure that they convert it. Let's see, you've got to do your temperature. So I'm looking right here, R, now we got to do our temperature. It's at 298 K. 298 K. Oops, K, sorry. Let's see, what else we got to do? The ln of the Q. And then you've got to do natural log of 9.3 times 10 to the negative third. Okay, guys, be careful how you tackle this. If I were you, I would do this expression first and solve for that number so that you can add it to that front value. Alright, here we go. 8.314 divided by 1,000 times 298. Alright, now times, open parentheses, natural log. That's basically 0.0093. Right? Yeah, 0.0093. Close those parentheses, ba-bam. Okay, I get negative 2.2 for this back value back there. So you have negative 33.3 minus 2.2. I get approximately, for the whole thing, delta G, I get approximately negative 35.5. Hope I did it right. Ooh, I did it wrong. What did I do? Try again. .314 divided by 1,000 times 298 times ln 0.0093. Ah, this gives me negative 11.6. Okay, so let's take that front value, negative 33.3, and then minus the additional 11.6. Okay, I get delta G, negative 44.9. Watch your units here. We got kilojoules. Okay, and that would be per molar just for the overall reaction. So our answer agrees with what we got in the book. Very good. Alright, let's go on to sample exercise 19.12. Okay, calculate an equilibrium constant from delta G. This is going to be a very famous equation for you guys to really try to remember. It says, use standard free energies of formation to calculate the equilibrium constant K at 25 degrees for the reaction involved in the Haber process. Alright, so all we need to know is that for sure we have an equilibrium. They didn't give us any values for like the pressures or anything, so we know that this thing is at equilibrium. That's one thing to establish first with this particular question. They gave us the standard delta G, which is great, and all we need to do is to figure out the equilibrium constant K. Please keep in mind that your equilibrium expression is always the products over the reactants. So this will be NH3 squared over N2 and then H2 cubed. Okay? Now this is an incredibly important formula. It says solving equation 19.17. Equation 19.17 is on the top of page 829. Super, super important one. Technically, K is equal to E to the negative delta G standard over RT. Okay? Alright, so all we have to do is start plugging in these incredible numbers. If I were you, I would tackle this by trying to solve for this number first. So negative delta G standard over RT. Alright, for us, the negative delta G, see, they already gave us delta G is 33.3 kilojoules per mole. Alright, when you're using R in the formula, you really need to go back to the joules. Alright, so if you're given, because the value of R has a specific value system, it's 8.314 joules per mole K. So looking at those units, it's pretty obvious that when you're using this value for your R, you need to make sure that your delta G is not in kilojoules but joules. So we're gonna, it says negative delta G and you already have a negative value for delta G, so I'm gonna do 33,300 joules over 8.314 times the T. It's at 25 degrees Celsius, so that's 298. Alright, let's see what this number is. So 33300 divided by 8.314 times, I'm opening my parentheses on the bottom there, 298, close my parentheses. Alright, I get about 13.44. Now, the key is just to use your answer in the next part. So look above ln, that's called natural log on your calculator. You should see an e to the x. Hit that, and then just plug in your answer from the previous part, and then you should be able to get your K value. And it's a rather large number. I get, and that's okay, remember K values can be extremely high. I get, wow, 68733, and if you round, 6. Holy bejeezers. And remember, K has no units. I'm looking at the book, and they rounded this to be 7 times 10 to the 5th. And that's totally fine, they just rounded up. Final answer. And since that equilibrium expression is extremely high, or since the K value is extremely high, basically you need to remember what that means. When your K value is much larger than 1, who's favored, the reactants or the products? The products, of course. Okay, this simple integrative exercise on the top of page 831 is a fantastic example of throwing together equilibriums, Hess's law, etc., etc., etc. I would strongly recommend that you check this guy out. Obviously, you need to work through a few problems by yourself in order to really understand. So one of the things that I would also suggest is that you look at some of the practice exercises at the bottom of the sample exercises to see if maybe you can solve a few of those on your own. But I'm done for now. Those are the two most important equations in this particular section. That would be equation 16, where it's delta G plus RT ln Q. And then obviously this other one where it's the equilibrium is equal to e to the negative delta g over RT. Alright, those are the two very important equations in this particular section, and guys, I'm done. Bye-bye.